Hi there, thanks for joining us on another episode of Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley, your host, and it's always good to have your company. Wherever you are, whatever you're doing, you might be in traffic, you might be in bed, staying awake. We generally put people to sleep, but staying awake. Or you could be just hanging around the house doing whatever you need to do, vacuuming, mowing the lawn. Yeah, all of that. Coming up in this edition, we're going to be talking about fires on the moon. What? How? Yes, it's a thing. Yes, it is, Geordie. We're also talking interstellar glaciers. Wow. The Mayan calendar and another Artemis 2 record that's been set. We'll find out all about it on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Back again to help us understand all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. Good to see you and good to speak with you on this chilly day.
What's up Geordie's nose today?
I think somebody's just arrived at the door.
That's usually how he welcomes them.
Yeah,
yes.
It is. It is. I might just need to go and check, actually, if you don't mind.
Oh, okay. Yeah, we can do that.
Yeah, you can talk to yourself for a minute.
Yeah, I'm very good at talking to myself, yes. Geordie's, I don't know what kind of terrier he is. He's a tiny little dog, but he's very, very loud. And whenever anybody turns up, he absolutely goes off his buns. And when Judy and I visited there late last year, we were welcomed by Geordie tearing down the stairs and barked like a maniac. But, yeah. He's harmless. He's absolutely harmless. All is well, Fred? Is he okay?
Yeah, well, he's all right. Yeah, he's the people who turned up at the door. Nobody opened the door for them, so they just let themselves in. That's all.
Oh, right. Okay, that
they're well known to us. They're coming.
Yeah. Queenslanders do that a lot, apparently.
Oh, do they?
When we moved to Queensland in 1987, after we got married, our neighbours walked in and introduced themselves.
Really?
And we thought, oh, that's so weird. But no, it's not. It's just the way Queenslanders are up in the northern tropics.
Yeah.
Completely different mindset. But you get used to it. It's a lovely lifestyle. Shall we get down to business, Fred?
Well, I suppose so.
All right.
If we must.
we probably should.
Yeah.
Let's start off with this story about fires on the moon. Now, I've looked at the moon many times. I've never seen any brush fires or bush fires or forest fires or, dune fires or mountain fires or crater fires. I got a suspicion this has got something to do with something humanity's going to do when they get on the moon.
Yep.
Let's talk about this because fires on the moon sounds a little bit, impossible, but it's a thing, or it will be.
It is a thing. It's a thing, and it's all about understanding how fires burn on the moon. It's something called the Flammability of Materials on the Moon experiment, otherwise abbreviated to FM2, developed by NASA in a number of their research centres, the Glenn Research Centre, Johnson Space Centre, Case Western Reserve University. What they're doing is they're sending what's called a self-contained combustion chamber to the moon, and it's going on one of these commercial lunar payload services flights that we sort of know about from discussions we've had before, where basically private companies provide hardware to send on robotic missions to the moon to set up things for when humans are exploring the moon a few years down the track. So it's all about safety, actually, Andrew. That's the bottom line for this. It's the motivation, because there is a gap in our understanding of how fire works. And that is because we understand how fire works here on the Earth, how the convection brings oxygen into the flame and keeps the fire burning. We understand how it works in zero gravity because experiments have been done on the International Space Station that allow scientists to estimate basically what the behavior of a fire would be in zero gravity. Apparently a candle flame in zero gravity is just spherical. It's a sphere.
I read that. That's strange. And I mean, we all know how horrible fires can be in terms of space travel. There've been tragedies over the years. Apollo 1 in particular, but there've been other incidents with fires and certain issues. But what happens on Earth and what happens in zero G, we know about. What happens on the moon?
That's what we don't know about.
Yeah,
and so that's the reason for these tests, because scientists have actually raised concerns about the way fire might behave on the moon, because it is different when you're in 1/6 of the Earth's gravity, which is basically lunar gravity.
Yeah.
There is a standard that is measured by NASA in terms of how things burn. It's called NASA-STD-6001b, and it's what's called a vertical burn test. And I'm reading now from a Space Daily article that describes this all very nicely. The current standard is a vertical burn test. A 6-inch flame is held to the bottom of a vertically mounted sample. If the flame climbs more than 6 inches up the sample, or if molten debris drips off and keeps burning, the material fails. It's a straightforward, repeatable procedure, and it's kept crews safe on Shuttle, International Space Station, and every commercial vehicle that has followed. The test has hidden assumptions baked in. The buoyancy-driven convection will behave the same way in flight as it did in the lab. For low Earth orbit, engineers have patched around this assumption with experience. For the lunar surface, there is no equivalent flight heritage to fall back on. In other words, we don't have any experience of how things behave in 1/6 gravity. So, yeah.
And
so it's,
I would assume that knowing what we know about fire on Earth and in zero gravity, with a little bit of gravity on the moon, it'd be different again.
yes, that's right. It's once again looking at the Space Daily piece, which is very, very nicely encapsulates what these experiments are about. There have been tests done inside uncrewed. Actually, they were the Cygnus ones, not the Dragon capsules, Cygnus cargo capsules, before they re-enter and burn up in the atmosphere. There have been what are called Sapphire tests, the Spacecraft Fire Safety Series. I think you and I spoke about that probably a couple of years ago. So what you do is you deliberately ignite samples of the material and look at how the flames behave. And sometimes actually they spread in the opposite direction to the way the airflow is coming. And also apparently they burn hotter on thinner materials. And that's all great, but that's microgravity. That's effectively zero gravity. And it is a different physical regime, as they put it, from partial gravity combustion, which is what we will experience on the moon. All these items, once again, a very nice summary here. The flame shape, the flow structure, the soot chemistry, and the spread rate all respond non-linearly to the gravitational acceleration. So you can't really, it's not something you can simulate. You can certainly simulate weightlessness, either by dropping things off big towers. That's one way of simulating weightlessness. Yeah. And it's what was in Einstein's head when he worked out the general theory of relativity, how gravity works. And then there are those parabolic aircraft flights that we often refer to as the vomit comet for humans. But none of those long enough period in order to simulate how things go when something catches fire. And of course, they're all microgravity. So this FM2 experiment is designed to be self-contained. It's a sealed chamber, contains 4 solid fuel samples, and they will go to one of these commercial lunar program landers on the surface. And apparently the burning samples are lit one after another, and there are all sorts of cameras and radiometers and oxygen sensors, temperature gauges, all of that stuff to look at the flame geometry and how much heat comes from it, how much of the oxygen is consumed. So all that is going to teach us what might happen if something went wrong when you have astronauts walking on the moon. If you have some sort of habitat where a fire is induced or catches fire or whatever, we should, from these experiments, we should know how to deal with it, which we don't at the moment.
Yeah. One of the points in the article I thought was interesting was that there could be materials that exist on Earth that are certified, A-grade fire retardant, nothing to worry about here. But that might not be the case with the same material on the moon.
Exactly, that's right. So that's what this is all about. And it's common sense, really, when you think about it. It's a lot better to send a self-contained experiment to the moon rather than getting somebody standing on the moon to light a match in a habitat and see what happens. That will not be good.
And I suppose long term, we're going to see all sorts of facilities on the moon. We're going to have, as you said, habitat, but there'll be labs, all sorts of spaces for all sorts of different things, probably things we haven't even thought of yet. There'll be, they're talking about making rocket fuel on the moon. Now, there's a fire hazard.
If ever there was one, that's right. If you're separating hydrogen and oxygen, when they come back together, there's a fire hazard. You're absolutely right.
Yeah, so there's a lot to take into consideration. So it's obviously something that they really need to figure out, and this sounds like a very good way of doing it, a controlled experiment. And does it say when they're planning to do this? It shouldn't be too long away.
No, that's right. I think it's on an upcoming one of these commercial flights. I can't see a date in it in this piece, but I'm sure we'll find about the results when they've actually happened.
Yeah, indeed. All right. If you'd like to read all about it, you can find that story at spacedaily.com, and you could probably find it on the NASA website as well. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Houston, Tranquility Base here. The Eagle has landed.
Space Nuts.
Now, Fred, we move from the moon to beyond. We're going way out, in fact, to interstellar regions of the universe, where NASA has discovered galactic ice. They're describing them as interstellar glaciers.
Indeed, that's right. So yes, from fire to ice, it's almost like being on Iceland, where you've got them together. And this is a story that comes from research that has been done using a spacecraft that you and I think we talked about it when it was launched, but we don't often mention it, and it is producing some quite significant results. It's called Sphere-X. Which is an acronym for Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer.
I would have guessed that.
Yeah. Yes, I'm sure you would if you were, had 20 years to think about what it might be, because I certainly wouldn't. But what it's been doing is, it's basically a survey spacecraft. It's got wide-angle telescopes. It has... It's basically, it takes images, but it takes them through, I think it's 102 different color filters, which these color filters are centered on key wavelengths in the spectrum, which allows you to image, see where all the iron atoms are, see where all the calcium atoms are, see where all the hydrogen atoms are, see where all the oxygen atoms are. All of that stuff comes from this ability to see the sky in, as I said, 102 colours. They're in the infrared, so it sort of mimics the James Webb Telescope. It's, however, as I said, a wide field telescope, which means it's doing surveys rather than homing in onto small areas of space where you want to magnify things so you can see all the fine detail. It was launched only a year or so ago, March the 11th, 2025. And it's already sending back some really quite spectacular results. So by the end of last year, it had completed the first of its all-sky infrared maps of the sky, of the universe, basically. Mm-hmm. And it's basically measured hundreds of millions of galaxies. It does it essentially in 3 dimensions rather than 2. An imaging telescope, you might think, can only see everything as if it was plastered on the celestial sphere, and that's an imaginary concept of where you say everything's at the same distance and it represents a sphere, and you can measure the positions of objects on that sphere very accurately in a science we call astrometry. But with all these 102 filters, you can also use this instrument to get estimates of redshift. And by that I mean effectively the way the spectrum of a distant galaxy is shifted towards the red end of the spectrum. And you can do that by choosing your filters carefully so that as certain features in the spectrum of a galaxy drop in and out as the redshift increases, you could get an estimate of what the redshift is without actually making a spectrum. It's a technique that's been known for many years, essentially called photometric redshifts. That's what we call it. So what they're doing is basically measuring the 3D positions of galaxies by the hundreds of millions, and that will tell us a lot about the state of the union in galaxies at very great distances as well as the nearby ones, and it'll tell us about the evolution of things like the amount of water that there is in a galaxy, the amount of ice, essentially. But they can also use this instrument not just to look at distant galaxies, but to look at the gas clouds in our own galaxy. And that's where this story comes from. They've looked at what we call molecular clouds, which you might not be surprised to hear are clouds of molecules. And they're where we think stars are born, giant molecular clouds. They've looked at some of the regions of the Milky Way which are richest in these clouds of gas. And essentially used the fact that infrared can penetrate dust rather well, at least near infrared can, as we see when we look at some of the pictures from the James Webb Telescope. That dust penetrating ability allows you to see deep into some of these giant molecular clouds, which are otherwise opaque to visible light. And then you can look at what sort of chemicals are there and what sort of ices there are in these clouds. And the ice, we know from other studies, the ice tends to form on dust grains. These are tiny dust grains. We call them dust. It's really smoke in space, because smoke here on Earth is solid particles, very, very tiny. That's how dust exists in space, in these very tiny particles, which are often coated with ices because the ice condenses on these cold dust particles. One of my former colleagues, somebody I actually studied with when I was at uni about 100 years ago, has spent his career in the United States looking at this kind of thing, looking at interstellar dust and interstellar ices. I don't think he's actually involved with this research, but he would certainly understand, and probably knows the people who are working on it would understand the results. So what they found is a whole range of different molecules, as well as water ice. There are some of the complex molecules like polycyclic aromatic hydrocarbons. And these are things that are, they're carbon containing, which is why they are called organic molecules. And finding those really gives you an insight into the chemistry that goes on inside some of these giant molecular clouds. And indeed, we know from other studies that some of those ices represent the building blocks of life, that we find all kinds of molecules that are important in life processes. So we haven't discovered life yet, but we've discovered the building blocks. And the point I was going to make, the point of this story, is there are huge quantities out there, more than anybody expected.
Yeah, we have talked about the fact that water is plentiful in the universe. That's certainly something that's becoming more and more evident. But this sheds a whole new light on it. Like it's out there in abundance.
Exactly, that's right. As you and I have said many times, the most common two-element molecule in the whole universe is water, H2O. And so it shouldn't surprise us that we've got ice everywhere. It's the same in our own solar system. We didn't know until comparatively recently that ice is abundant, particularly in the moons of the outer planets, Saturn, Jupiter, Saturn, Uranus and Neptune. They've all got moons that are very icy. And then you go out to the Kuiper Belt and the trans-Neptunian objects, they're all icy too, as are the comets that reside in the Oort cloud. So it's everywhere. Water is absolutely everywhere.
Yeah, and the liquid oceans in the ice moons, and the list goes on. And of course, the way water is ended up in certain places, one theory we talked about some time back is that when Earth formed, the water was already here, because like this, where water is attached to those dust particles or dust molecules, same with all the material that made Earth. And it's just eventually, as conditions changed, seeped into the places where it's now become oceans and clouds and rivers and created a whole ecosystem.
Exactly, that's right. Yeah. That's certainly. So we think maybe the Earth's water has two sources, one of which you've mentioned. It's actually hydrolated rocks that formed the Earth, but also the possibility that some of it came from comets. And we've discussed one of the problems with that theory, in that sometimes the comets' heavy water to normal water ratio doesn't match what the oceans of the Earth have. And I think there are some comets that do, but some don't. So it's kind of open question.
Doesn't match on Mars either, compared to Earth.
I believe not. That's right.
Yeah. It's all fascinating. I love it. Really. You didn't think water was so interesting, but it's pretty amazing stuff. Yeah. Great story, this one. You can read it at phys.org, or you can read the paper that's been published recently at the Astrophysical Journal. Space Nuts, this is, with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all four systems and keying with a go.
Space Nuts.
Righto, Fred, a couple of stories to finish up, a couple of quick ones. I was reading an article the other day and it just sort of jumped out at me. A new paper has been published after a study into the way the Mayans used to calculate time and used mathematics to predict things that most civilizations would have thought were pretty random and damn scary, like eclipses and seasons, and the list goes on. But what the Mayans did was probably far superior to most other civilizations. Their mathematics was beyond comprehension for most of us, I think. This is all brand new information. I know we know about how clever they were, but this kind of sheds a bit of new light onto it by the look of things.
That's correct. It's the result of some research that goes back to a document called the Dresden Codex, which is essentially a manuscript that dates from the Maya civilization, which was actually extremely long-lived. I think it sort of kicked off something like 2000 BC or BCE, and lasted until the 1600s AD or CE, Common Era. And so that's perhaps a hint as to why their mathematics and astronomy were so effective, because they had a long, long time to count the years between certain events, and to do that over many, many years, so that you get a really accurate idea. And the kind of thing I'm thinking of, Andrew, is the lunar cycle. The moon has a cycle of 18.6 years, and on that scale, eclipses more or less repeat throughout the year. They don't exactly repeat, so you don't get total eclipses occurring in exactly the same place. But you can use that cycle in order to predict when there are likely to be eclipses. So if you've got a long established civilization with a long memory, that 18.6 year cycle would be well known and well understood. And I think what's made the particular study that we're talking about, it's published in the journal Science Advances, is that some of the tables that are in the Dresden Codex have now been interpreted as being the method by which the Maya people actually did do things like predicting eclipses. Yeah. And it differs from what people thought happened. People thought these tables were just sort of one-off things that didn't really talk to, have anything to do with each other, the tabulated information. But it now looks as though it's much more clever than that, a kind of iterative approach with tables that overlap, and basically, as time goes on, you eliminate any kind of errors that might be there until you end up with something very accurate indeed. So it's quite an interesting story for people who are interested in archaeoastronomy, which we are, of course, on Space Nuts.
Yeah, I think it talks about the Mayans having two completely different systems, but when they put them together and looked at them, they went, "Hey, wait a minute." They work together, and they are so incredibly accurate, and it opened up a whole new realm of understanding about how the Mayans did what they did. And I suppose when you think about it, they had 4,000 years, as you said, they had a long period of time to collate this data. So, pretty amazing stuff. And it brings me back to that old chestnut that we assume we are all knowledgeable. We are the cleverest humans that ever existed. We're not. We're no more intelligent than the first humans. We've just progressed over time to reach the point we are. But the Mayans are exhibiting an intelligence that predates the modern era, if you like, and that they've shown that the intelligence of Homo sapiens is long-lived. It's not just something that's happened in the last few hundred years. It's always been there, I guess is what I'm saying.
Yes, that's right. So that's Homo sapiens. That's right. We are gifted with a brain of 100 billion neurons, which can still outdo computers and AI, although, of course, AI is catching up, but it's still not human, and I don't think it ever will be.
I hope not. I hope not. Judy and I read an article the other day about how they're going to use AI robots in nursing homes in the not-too-distant future to help people with simple things like communication, just having a conversation, because they get lonely. And they're going to use AI robots to do things like that. They'll be able to have intelligent, one-on-one conversations with a human being. Like this, that blows my mind. I know you can kind of do that at the moment with, your Google Homes and all these, but this is a whole new level.
Yes.
And it looks like they're going to roll that out in parts of Australia in the not too distant future. So, it's a brave new world. Just I hope they remember the 3 laws. We better not forget that. Yeah,
of robotics.
Yes, the 3 laws of robotics.
Yeah.
Yeah. But if you want to read about that story, it's at futura-sciences.com about the Mayan calendar and their mathematical brilliance. One quick one to finish off, Fred. We're going back to Artemis 2. We talked about not so long ago, not like the whole mission and everything they did, but the fact that the astronauts on that particular mission were the humans that achieved the furthest distance from humanity in history because of how far out they had to go to loop back around the moon. But now they've made another quirky little discovery about a record that was set that somebody just by chance decided to follow up and went, oh, hang on a minute, I've actually found something. What's this one about?
Oh, well, it goes back to one of the veteran commentators on space flight and satellites, somebody whose work over the decades has been invaluable in telling us how crowded space is and things like that. His name's Jonathan McDowell. He is always, I think his head is full of numbers that relate to spacecraft. But he noted that there is something different from what was being widely touted during the Artemis mission, and that is that the distance between the humans on board Artemis and the humans on the International Space Station was a record for the separation of humans, and it was actually 419,581 kilometres. That's the integrity to International Space Station distance, 260,715 and a half miles, if you want that. But Jonathan McDowell took a closer look at what was in space at the time and realised that the Chinese space station, Tiangong, was further away with its 3 taikonauts on board. In fact, it's about 62 kilometres further away at 419,643 kilometres. So that's the maximum separation of humans. It was between Chinese taikonauts on Tiangong and the Artemis crew on board Integrity. It's very typical of Jonathan McDowell to pull little statistics like this out of the air. But he was interviewed by Space.com, and they asked him lots of questions like, is this significant, this Artemis 2 record? And what he said was, I think, quite profound in its own way. I think the significance is that it's the beginning of a shift from how far from Earth are our most distant people to how spread out is human civilization. And he said there may come a day when it's Mercury to the moons of Saturn.
Yeah.
Which is true.
Yeah, I was going to actually suggest that, when we go to Mars, the records will be set there, and it'll just keep growing. Yeah, and I'd say in the next 100 or 200 years, we'll probably have people on Mercury at the same time as we have people on Pluto or something like that. It's very possible. So the numbers will just keep growing.
Yes,
and in time to come, they'll probably go beyond that too. Who knows?
One day, perhaps, if we don't do ourselves a fatal injury before then.
Yeah, like bust a pufu valve as we're running around the solar system. Yeah, who knows? Great story. If you'd like to read about the statistical separation of human beings, it's, as Fred said, it's space.com. And we're all done. Fred, thank you very much.
Great pleasure, Andrew. Always good to chat over these things, and I look forward to talking about some questions with you at some time down the track.
I think we'll do that very, very soon, probably sooner than most people think. Thanks, Fred. Professor Fred Watson, astronomer at large. Don't forget to visit us online while you're on the interwebs at spacenuts.io and spacenutspodcast.com, and check it out. You might like to become a supporter. Just click on the Support Our Podcast button. You might like to send us a message or a question. Just hit the AMA button up the top. That's Ask Me Anything. You can sign up for Astronomy Daily. You can visit our shop and buy yourself a hoodie. It's coming up on winter in Australia, so, you might need one of those. Or you can buy yourself a T-shirt as it gets warmer in the Northern Hemisphere. And plenty of other stuff at our shop. And, it's all at spacenutspodcast.com. And thanks to Hugh in the studio, funny story, he saw us log in, so he logged out. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.